Let's get back to star formation, and let's consider the formation of a Sun-like star, a one solar mass star. So what's going to go on? We've got an initial molecular cloud. It's going to have a low density, let's call it 10 to the 10 particles per meter cubed. It's pretty big, a million times the size of the Sun. And basically you're going to have something that once it starts collapsing, there's not much impedance, there are not that many collisions, so it's going to collapse by free fall. At this point, the pressure is increasing, but the pressure is nowhere near high enough to balance gravity, so gravity is winning. And basically, as long as it's easy for the photons to escape, so you've got this thing that the cloud is collapsing, it's accelerating the particles getting faster, they can collide with each other, and so basically you've got this thing is becoming kinetic energy and thermalized, and it will release energy, because everything that has energy releases energy, and those photons escape. And as long as there's not much to stop it from getting out, then those photons just go off at the speed of light and leave the cloud. And so it continues to collapse. But at some point it becomes optically thick. That is to say that it's not so easy for the photons to get out. And we'll get into the details of how that works later. But basically you've got something where you're trying to collapse this thing in, but it's getting too hot, the pressure is going up, and it's hard for the photons to escape, and so you end up with a balance. So the photons aren't escaping, the process starts heating up, and so the rise in pressure, you get hydrostatic equilibrium. But it's going to give off energy. It has temperature, it's going to give off energy. So basically, about 500,000 years into the collapse, it's going to be a really fast collapse, and then it's going to slow down because it has to lose energy in order to go further. So the temperature is going to keep going up, but it's going to do it slowly because it has to lose energy each time it wants to shrink. And we'll come back to that idea later. Once we get to 2000 Kelvin, approximately, all of the molecular hydrogen is going to be converted to hydrogen atoms, and that uses up some energy. And so instead of continuing to heat up, it's still shrinking, but now it's using energy to do the dissociation, and so it's not heating up anymore. And so the pressure is not rising so fast, and so now gravity really takes over and collapse goes fast again. Once you've got rid of all the molecular hydrogen, you've used up all of the photons you can in dissociating, then the temperature can go back up. Those photons are going back to providing energy for the cloud, and you get back to hydrostatic equilibrium, and we go back to this, what we call a quasi-static model. Basically the idea is that you've got hydrostatic equilibrium, but you're glowing, and so you're losing energy, and as you lose energy, the temperature goes down, so the pressure goes down, so gravity wins. But gravity wins, the temperature goes, the potential energy converts to kinetic energy, the temperature goes back up, and so it's constantly reattaining equilibrium, and so that keeps it slow. But let's look at this in detail in terms of the Hertzsprung-Russell diagram. So here I've got my HR diagram, I've got my temperature and my brightness, and this is for a one solar mass star, so it's going to end up at G. And I've got these different places along its collapse that we're going to talk about. So this is starting from, you've dissociated all of the molecular hydrogen. So we're at A. From A to D, we're basically in free fall. And so what we're getting is both the luminosity and the temperature are increasing. So even though we're using up energy we've used up all the energy to do the dissociation, we're now at the point where the energy is all going into increasing the temperature. So it does both. The radius is decreasing, but because the temperature is increasing and temperature is a bigger factor, remember it goes as T to the 4, whereas the radius, it only goes as the radius squared, so the luminosity does go up. And if we look at this, we've got something where we've gone from point A to point G, and we've gotten from point A to point D, and from point D to point G. And so how is it changing? Well, we can actually work this out. Remember, we know what it is in terms of the size of the Sun from its blackbody radiation. And so we can basically work out, well, at this point, what size is it compared to the Sun? At this point, what size is it compared to the Sun? And here we have those calculations. So the size of the Sun is at RG, that's where it's become a main sequence star. At A, it's about 6 times the size, and it's only shrunk a little. It's only shrunk down to 5 times the size when it gets to D. So at D, this is when we get the back to hydrostatic equilibrium, okay? And we've got a surface temperature that's 7,000, but it isn't hot enough yet inside to do any sort of fusion. And what happens here is that, so we haven't really talked that much about opacity, but what really matters for getting the energy out is how opaque is the material. And that depends on temperature. So at low temperatures, you have high opacity. It's very hard for the photons to get out, and so you'll tend to retain the energy. But as it heats up, you can then change it over so that it gets to high end. As it heats up, you can get less opaque. So when we get to D, the opacity is high, but that means that it's really hard to move the energy. And we'll talk about how things are moved radiatively versus convectively in another section. And so at this point, what you're doing is the energy is being moved by convection. You've got, it's so opaque that you have to move the material and not just move the photons. And to move convection currents, you're actually using some of the energy to drive the motion. So it's not just that you've got energy in the particles, you have to drive those currents, those convection currents. And when the temperature drops, the luminosity drops, and it's still collapsing. And so the radius is decreasing, so that adds into the effect. And so this is why from D, you start to get this, this change in the brightness that goes down. Okay, it's going down in temperature too because we're using some of the energy. Eventually, the opacity goes down. So basically, as the temperature goes up, the opacity goes down. We'll get into all the mechanisms by which this happens, but basically, generally at high temperatures, you have lower opacities. So as it's heating up inside, it's going to get to a point where it becomes less opaque, and when that happens, it's very easy for the energy to escape. So the convection switches off, and we start moving the energy as photons. And that means that the temperature can increase again, and so does the luminosity. So that's basically when we get down to here. Okay. So we're increasing, and then at G, the internal temperature gets high enough that we can start doing nuclear reactions. We're doing the PP chains, sticking hydrogens together to make helium, and at that point, that energy production is what is used to sustain hydrostatic equilibrium, and so the core collapses, and now we have a main sequence star. Now, for more massive stars, it looks like we do something different, but actually it's a similar process. So we've got, for low mass stars, we have something that it seems to decrease in luminosity but doesn't seem to heat up very much at the surface. Whereas for the high mass stars, we've got that the luminosity doesn't really change very much, but the radius gets smaller and the temperature gets hotter. And so what is the difference between these two? Well, actually, the issue is that when we're looking at it on here, we're looking at a very, very short time scale. And so we're looking at this path, and it's just not got enough detail in it. So all stars are going to follow a very similar path, but the drop that goes from A to E is so fast that that spike is such a short time that actually we might not notice it. Okay? And in a more massive star, it happens so fast that it's actually dominated by going from E to F. So basically, you can see you start here and you go to here, and you end up with something that doesn't look like it's changing much at all. And in fact, for the high mass stars, you can switch on hydrogen burning before you even reach the main sequence. So this is actually just another version of this. So I've got another HR diagram. These are called Hayashi tracks when we're plotting how the star changes in brightness and temperature on the Hertzsprung-Russell diagram. That's Hayashi tracks. And so we've got here with the low mass stars, they're actually moving most of their energy by convection, and so it just goes down in temperature. It just goes down in luminosity. And in general, these heat up so much quicker that they go into radiative mode faster and they end up with core fusion faster. And so this is one of the reasons that you get this difference. Okay, so we already talked about Varial theorem in a different clip, and I want to bring that into play when we're talking about this formation of a star. So we're considering our star formation, and as the protostar collapses, the gravitational energy is released and is transformed to thermal energy. And so the protostar heats up, and you lose energy by radiation. We've talked about that with respect to the Hertzsprung-Russell diagram. Once half of the gravitational energy is lost, and the other half is stored in internal energy, then the hydrostatic equilibrium is attained. If more than half of the gravitational potential energy goes into kinetic energy and is not lost to radiation, then the gas heats up and it increases the pressure, and that will make the star expand. The expansion turns kinetic energy into gravitational potential energy, and so the gas cools a little, which decreases the pressure, and you also expanded a little, so your density is lower, and so it's going to gain hydrostatic equilibrium. So basically what you've got is if you overshoot and you get too much pressure because you converted too much potential energy to kinetic energy, it will bounce back. It will then expand again because it gets too hot. So it has this natural regulation. So if you want to have a cloud, a gas cloud, collapse down into a star, it has to get rid of thermal energy so that the gravitational forces can win, so that gravity beats pressure. It doesn't have to be a huge change. So what you can, again, this is thinking about this from the point of view of what's really happening. You've got hydrostatic equilibrium, but it's still not fusing anything in the core. But now it's glowing, and it's lost just a little bit of energy from glowing, and so the temperature goes down, so the pressure goes down, so it goes down just a tiny weeny little bit, and that will regain hydrostatic equilibrium. But it continues to glow, and it continues to give off energy, and so it will continue to collapse. So basically you are constantly regaining that balance between gravity and pressure as energy is radiated away. And so what that does is that limits how fast you can make the star contract. If it could just contract under gravity, it should be able to do it fast. But because you have to lose this energy, because pressure is playing a force against gravity, you really can't do that. Once it reaches the main sequence, then you have the radiative losses are exactly balanced by what's being made in the core, and so you no longer have to shrink to maintain the pressure. And so this is how we define the start of the star's life on the main sequence. So taking this into account and thinking about Varial theorem, how long does it take for a star to collapse? So remember, we already worked this out in the Varial theorem section, that the gravitational energy released in the formation of a star is given by this equation. It's the integral over the radius of the star for these mass elements and the mass that it's falling onto. For simplicity, and because this gives you a rough idea of what's going on, we're going to assume that we have constant density in that intersection that the shell is falling onto, and we're going to get the mass is then given by the density and the volume, and so we're going to plug that in. Okay? So now we've got something where we're assuming that the density is constant, so that's not going to change. So now we've just got one variable of r, and so we can integrate that, and we've integrated it and put in the limits with respect to r, because the 0 just goes to 0, and we get something that looks like this. And so what I've done is I've just rearranged this. I've taken out a 16 pi squared r to the 6 in order to get rho squared, etc., in order to get out this term, which is just the mass, right? This is the volume of the star and the density of the star. And so this is what we're left with. And so we end up with this thing that tells us what the potential energy of this star is based on the collapse from infinity. Okay? So that's our equation for the potential energy. Let's put in some real values. We put in the mass of the sun and the radius of the sun, and we find that we have about 2 × 10⁻41 joules. 2 times 10 to the 41 joules is the energy that was gained in the collapse from a big cloud down to a star. And so half of that has to be lost, right? Half of the 2 times 10 to the 41 joules has to be lost during contraction. Now, again, this isn't entirely true, but it gives us a good ballpark estimate. If we assume that the sun has always had the same luminosity, so it basically did what the supergiants do, then we can do a rough estimate. We can say the luminosity is its current luminosity, and how long is it going to take to lose half of the potential energy, so a little over 1 times 10 to the 41 joules. So the collapse time is then given by this equation here, which is of the order of 10 million years. And so it should take, just based on the time it takes to glow and get rid of the energy, it should take about 10 million years. We'll get on to what the real impedance is, what it is that stops it from collapsing, in another section. This is called the Kelvin-Helmholtz time. This was actually the original estimate for the age of the sun before we knew that it was fueled by nuclear fusion, the idea of gravitational collapse for its age. And so this was one of the things that was suggested as how you could calculate the age. And it's now known as the Kelvin-Helmholtz time. And that's all we're going to do on this part of star formation, and we'll be getting into the energy transport next.